All right, guys, we're back with our second installment for improper integrals. If you've not watched the first part, that one's crucial, so make sure you go to that video and check it out. In this one, we're going to talk about integrating functions over a closed interval that are not defined at or between an endpoint. So this is another type of improper integral, one that has an infinite discontinuity. So the upper and lower limits are finite numbers. You don't have infinity there, but there may be an endpoint or a point in between where there's an infinite discontinuity. So basically it comes down to three cases. If the function's continuous on the interval a to b, but not at the endpoint, then you're going to have to define that as a limit as x approaches the right endpoint from the left. So this notation again is important because now we're dealing with one-sided limits. So if we have the interval from a to b, okay, and the function is defined at a but undefined at b, I'm just graphing on a number line here, then when we rewrite the limit statement, we're going to have to approach b from the left side of b. So we would do c approaches b from the left. If your limits are a and b, but the function is not defined at a and is defined at b, then you're going to have to rewrite it as the limit as c approaches a from the right. In the third case, where both the upper and lower limits result in infinite discontinuities, then you're going to have to do two separate integrals, split it at some point in between, and then let it approach one of them from the left and the other one from the right. So in the first two cases here, if the improper integral converges, that when the limit exists, otherwise the improper integral diverges. In the third case, the improper integral diverges if either of these two integrals diverge. It's now always important to check the domain of an integrand to see if it's not defined at either endpoint or in between. So a classic example would be the integral from 0 to 2 of 1 over x minus 1 squared. It'd be tempting to just anti-differentiate that, plug in 2 and 0 and subtract. The problem is at x equals 1, you have a vertical asymptote, so there's an infinite discontinuity. So this would be an improper integral of this third kind. Also, make sure you're using the correct one-sided limit. So here we have the area under the graph of y equals 1 over square root x, and we want to know, is that defined from 0 to 4? Now, previously we did the integral from 1 to infinity of 1 over root x, and we saw that it was undefined. But here we can't apply that theorem of 1 over x to the p because we're not going from 1 to infinity. So basically what we're looking at is the integral from 0 to 4 of 1 over square root x. And the thing with this is the function is undefined at 0, so we're going to have to rewrite this as the limit as a approaches 0. Now we're approaching 0 from the right-hand side, so you need to make sure you do a one-sided limit there, of the integral from a to 4 of 1 over root x dx. So this is the limit as a approaches 0 from the right of 2 square root 4 minus 2 square root a. Remember, we already talked about how the antiderivative of 1 over root x is 2 root x. So I plugged in 4, plugged in a. 2 root 4 is going to be 2 times 2, which is 4. And as a approaches 0 from the right, this is going to approach 0. So this area is equal to 4. And yes, the area is defined and the integral converges. Next one we want to look at is, does the integral from 0 to pi over 2, tangent x, converge or diverge? Tangent is undefined at pi over 2, so we would have to rewrite this as the limit as b approaches pi over 2 of the integral from 0 to b tangent x dx. And if you think of the interval just on the x-axis from 0 to pi over 2, you have to approach pi over 2 from the left. So it's very important to put that little negative there to have the correct one-sided limit. Now, we're going to anti-differentiate this, and the antiderivative of tangent is natural log secant. So this is the limit as b approaches pi over 2 of natural log of secant b minus natural log of secant 0. Now, natural log of secant 0, secant 0 is 1, so this is 1. So natural log of 1 is 0. Secant b, natural log secant b approaches infinity because secant b, as b approaches pi over 2 from the left, that approaches infinity. So this one diverges. So this is one I was speaking about previously. We want to know, does the integral from 0 to 2 of 1 over x minus 1 quantity squared diverge? It's tempting to say that this is going to be integral from 0 to 2 of 1 over x minus 1 squared dx. The antiderivative of that is negative 1 over x minus 1. Plug in 0 and 2 and subtract, so you have negative 1 over 1 minus negative 1 over negative 1, and you have negative 1 minus 1, so that's negative 2. But all of this is incorrect because at x equals 1, this function is undefined and has an infinite discontinuity. So we have to take care of that. So with this one, since the infinite discontinuity is at x equals 1, that's where we want to split this integral and rewrite it as the integral from 0 to 1 of 1 over x minus 1 squared dx plus the integral from 1 to 2 of 1 over x minus 1 squared dx. And then we would take each integral separately and evaluate it as a limit. So we take the limit as b approaches 1 from the left of 1 over x minus 1 squared dx. And this is going to be the limit as b approaches 1 from the left of 1 over x minus 1 negative. That's the antiderivative. Now we plug in 0 and b. So limit as b approaches 1 from the left of negative 1 over 1 minus b minus 1 minus negative 1 over 0 minus 1. Now, as b approaches 1 from the left, the denominator here gets infinitesimally small, and this goes off to infinity. So this diverges, because remember, you only have to have one of them diverge for the entire integral to diverge. And since the first one we checked diverges, we don't even have to check the second one. So this one diverges. Next example we want to take a look at is this doubly improper integral. The issue with this one is that the upper limit is infinite and the lower limit is an infinite discontinuity. So in this case, we're going to have to break it up into two separate integrals. We're going to do, or the limit as a approaches 1 from the right of the integral of a to going to pick a value between 1 and infinity. I'm going to pick root 2 because I know that the antiderivative is arcsecant, and root 2 is a value that arcsecant is easily evaluated at. And this is the limit as a approaches 1 from the right of secant inverse of root 2 minus secant inverse of a. And secant inverse of root 2 is pi over 4 minus secant inverse of a as a approaches 1 from the right is going to approach 0. So that's going to equal pi over 4. We also have to look at the limit as b approaches infinity of the integral. Here this is the limit as b approaches infinity of arcsecant or secant inverse b minus secant inverse of root 2. As x approaches infinity, secant inverse approaches pi over 2, and secant inverse of root 2 is pi over 4. So if we look back at this original integral, we can think of this as the integral from 1 to root 2 of 1 over x root x squared minus 1, plus the integral from root 2 to infinity of 1 over x root x squared minus 1 dx. For the first one, we got pi over 4 minus 0, so pi over 4. And for the second one, we got pi over 2 minus pi over 4. The pi over 4s cancel, and that area under the curve from 1 to infinity from the doubly improper integral here is equal to pi over 2. So we know it converges and equals pi over 2. Oh boy, that's a lot going on there. This last thing I want to talk about is the comparison test for improper integrals. So in some cases, finding the antiderivative of the integral can't be done. And under some circumstances, we can still determine whether the improper integral converges or diverges using the comparison test for improper integrals. So if two functions that are non-negative and continuous on the interval and f is greater than g, if f converges, then g also converges. If g diverges, then f also diverges. In this one, it's important that when you do the comparison test, the function that you pick to compare to either has to be the greater than one or the less than one, depending on if it converges or diverges to be able to compare it with. If the bigger function converges when it's integrated, then the smaller function, g of x, would converge also. If you're looking to show that a function diverges, then you have to show that g of x diverges, which is the smaller function. And if f of x is greater than that, it also has to diverge. We'll look at the improper integral from 1 to infinity of 1 over x to the 5th plus 1. So we don't know how to get the antiderivative of this, but we do know that if we have f of x equals 1 over x to the 5th, then g of x is going to be 1 over x to the 5th plus 1. And we could easily see that 1 over x to the 5th is greater than or equal to 1 over x to the 5th plus 1. If you cross multiply, you'd have x to the 5th plus 1 is greater than or equal to x to the 5th. You subtract x to the 5ths and you have 1 is greater than or equal to 0, which is true no matter what x value you plug in. For x greater than or equal to 1, which is important because that's where our interval is. It's from 1 to infinity. I'm going to compare it with the integral from 1 to infinity of 1 over x to the 5th dx. This converges because p equals 5, which is greater than or equal to 1. Remember the 1 over x to the p? And since that integral converges and is greater than the original integrand, the original improper integral converges as well. All right, guys, that's it for this video. Hope that was helpful to you. Take care.